I find that it is mentioned that I would be talking about fiber bundle model, but I think there are real experts like Alex and others who probably can tell some more details. I will of course introduce the fiber bundle model. Before that, I would like to discuss the fracture properties of disordered solids as fracture gets nucleated. I mean, in the sense that you have disorder in the solids or defects in the solid, and the defects are of various dimensions, and if you have a defect, then the elastic energy density, elastic energy around that, density around that gets affected, and this stress release region, whatever, we will come to the definite kind of things later. If they do not overlap, if they are far apart, if these stress release regions of various defects, due to various defects, are actually far away, and they do not overlap, then you have some kind of way to estimate the strength of the solid, which is kind of first introduced by Griffith, Alan Griffith, in 1940s or so. I don't remember now, maybe it is even earlier, and that was the starting point, and that gave the first idea how to proceed with nucleation of cracks. Just to demonstrate, I have produced a sample for you, and you can see that I have produced some defect. I mean, you can see that I have produced one defect, and I have produced another defect in this. You consider this as a solid, and I will put some stress on this, and you can see that although I mean I couldn't make it uniform, but you can easily see whatever I do, which defect is going to break first, I mean propagate first, I mean the bigger one. Well, so, and it is indeed, I mean that you can easily imagine that the stress that I mean if that would not be there, like here, there are also defects, but they are of kind of similar size and overlapping. So it's in a sense, in that sense, not dominant defect is there. So you can see that it could be, the stress could be uniformly distributed. I mean, the stress lines, you could see that you have put some stress, the sample is under some stress, and some kind of I mean stress lines would be uniformly distributed. But once you put some defect here, then this has to, this line will be sorry, this line will be somewhat like this, and far away, of course, there would be nothing. So if I have, for example, here this defect is not affecting, but now if I have a defect here, this will produce a region around it, but very soon that would be same, and then, so these regions are not overlapping. Now if they are not overlapping, you will see one of them is the weaker one or weakest one in the sample, and that would be, because I mean, as I said, there are many more defects than that I showed or indicated. There are many more defects, but so there are some very dominant defect, and as you rightly pointed out, that the bigger one will first fail. Now the thing is, what would be the stress value for this length, and I need another stress to break that one. This one was much bigger, when this was there, the sample was much weaker compared to this one. So in terms of the dimension of the defect, if you want to find out, one thing is that, of course, the stress is concentrating, and from there, and since it was a sharper one, the concentration can be infinitely large. I mean, compared to the stress that you, kind of impose on the sample. So just by making sharper, I could make this stress concentration here very, very high. But that doesn't mean that any stress would break that sample, because when there is a breaking or propagation, the new surface is created. That surface energy has to be provided from the elastic energy, because this is the only source. The elastic energy will be released, because if the defect goes further, elastic energy will be further released, and that energy must be at least able to provide for the surface energy of the new surfaces created. So the idea was that if I have a defect, just so that's the suppose, I mean, around the defect, this is the same sample I am showing under stress sigma. So, and let us assume that this is brittle one, in the sense that I have strain linearly proportional to stress. Okay, so sorry, this is, so strain is proportional to stress. So by some kind of modulus of elasticity is strain. I mean, you are assuming that this strain, I mean, and I am going to the breaking point, so in a sense stress is higher, but I am assuming that the system is linear or brittle, so that the elastic modulus is not dependent on the stress at all. Okay, so then what is the energy? Energy will be stress into strain will be proportional to sigma square by y. This is the energy density. So that would be everywhere. If there would be no defect, it would be everywhere. This would be the energy density. But the problem is, if I have a defect, as I demonstrated, there will be a region around which this energy density will be affected. First of all, you cannot support a stress here on the broken surface, so there would be a region around which this defect would be where the elastic energy will be affected. So let us assume that there is a geometry which need not be a kind of, I am assuming a circular cross section. I mean, you can have a width of this sample. Say the width of the sample is this. So I am just showing a cross section, and on this cross section, this defect region is some kind of circle with the length of the defect as the diameter. I am assuming that. I mean, you can do this calculation much better way later, but I will show that it will not. I mean, if you are interested in finding out what is the what is the form of, or what is the dependence on the dominant size of the length of the defect, then you will see that the exact geometry will not matter. This will be a kind of two-dimensional region of the cross section which will be affected, and I am assuming that two-dimensional region is a circular one with this as the diameter. But that is an assumption. You can change it, but what I would try to indicate that as long as it is a two-dimensional one, the dependence of the stress of this one or this one with respect to the length would not be, I mean, my calculation would not be affected by that assumption. So how to do that? It will be like this. So I have everywhere this, and I am saying that this region is affected. So now I assume that there is a further propagation on both sides by dl. So this region will be will all lose the elastic energy. Let us assume that. So there are 4 surfaces created, 2 here, 2 here. So, and let us assume that 4 length is dl, width is w, this is the area, and then surface energy density is say gamma of this solid. Then this much energy I must provide, otherwise this surface will not open up. Okay? So that must come from the extra elastic energy that is lost from this region, this annular region only. So that is sigma square by y into say some kind of 2 pi L dl into width. Now this at least must be greater than equal to this loss of elastic energy must be sufficient to produce provide this surface energy. If it has an extra, then there would be a crack growth velocity. I will come to that later. So for minimum propagation velocity, you need this minimum propagation with some non-zero velocity for the crack to grow. You must need this, and that is the sigma c that would be now. So these things are no longer there. This 4 you can forget, and 4 2 pi etc. So sigma c square goes as surface energy density times modulus of elasticity by L square root, okay, by square root of L. So this is the length of the crack that had been earlier, and if that has to propagate further, my external, I mean the stress on the sample must be this much. There are some prefactors. Now these prefactors depend on the precise geometry of the stress release region, which I assume to be circular here, so these numbers are coming. But if it is different, you have different. So this says that if it is brittle, that means there is no sigma dependence here, and of course surface energy density is constant. Then the nucleation stress that is required to propagate a defect of length L, or the minimum stress required, goes down with the square root of inverse square root of the length of the defect. Now, okay, these were checked in various things, and it was very interesting that just a simple nucleation calculation could give you this. So generally what happens is that I will generalize. In a sense, I have sigma square by y is the density of elastic energy density, because stress times strain. Then in a d-dimensional sample of L is the length of the defect. Typically the energy is of the order of this, must be equal to the surface energy density L to the d minus 1, okay? D minus 1, d is the dimension of the sample. So the surface will be 1 dimension less, plus this is order of magnitude kind of thing, some half mv square is the kind of kinetic energy of the crack. I mean, if you put more force, more stress, then the released energy will be more than this one, and then there would be a crack tip velocity. And then, okay, so then I can write like this: V square is equal to sigma square by y m into this, or rather, sorry, my minus gamma. I have taken this. Okay, L to the d remains, L to the d minus 1 remains. So I take okay, let me see, this has come here. So sigma c is, okay, so I take something common. And L to the d common. So what is this? This is sigma square minus gamma y. Okay, so m was here also. Okay, so that has gone by L. Yeah. Okay. Now that says, but this was identified. The surface energy density times this by this is the minimum nucleation stress that is required. So L to the d by m y into sigma square minus sigma c square, which can be written as sigma plus sigma c minus sigma c. Now sigma plus sigma c, suppose your sigma is very close to this, so it is actually around 2 sigma c into this factor is there, and into sigma c into sigma minus sigma c, and that says that V goes as, crack tip velocity goes as sigma minus sigma c to the power half. And that means if you take the velocity of the crack tip in this kind of situation against sigma, from 0 to sigma c there would be no velocity because the crack is not propagating at all, and then it will start growing as sigma minus sigma c to the power half. So dynamically, this is one would identify. This is not very obvious from here, but we would try to identify this is like a transition, like in a ferromagnet, for example, magnetization. I mean, if you take the ferromagnet, then what would happen is that magnetization, you know that, okay, let me draw the magnet. Ferromagnet is below the Curie temperature. So T is temperature here, T is temperature. So magnetization is 100%, so that is say 1, and from 1 it goes to 0. This is the Curie temperature, and I think many of us derived how this varies in the Curie-Weiss law. Okay, yes?
You consider only one crack.
Yes.
So the effect of other defects is there.
I am assuming that they are quite separated. I mean, the stress release regions are quite separated. So the only vulnerable one, we will come to this thing later. Yeah.
It will not be the case.
In
realistic system.
Yes, we will come to that. That would be, yeah. So when you have a real major defect, which is clearly identifiable, and that is kind of.
And second point is that this V, the velocity goes as sigma minus sigma half. Can we think of it as a dipping transition? Because you are applying the force.
Yeah.
And at some point it starts growing.
It is, we will have to come there, but I mean, maybe, I mean, I have to introduce deepening later on, I mean, okay. So at the moment, let us come to some example of, maybe very common example of magnetism and things like that, as Purushottam was mentioning, that we are very much, this is a very common example of a physical system having, okay, why ferromagnet is so important. You see, I mean, Weber long back, no quantum mechanics was there, Weber found that, I mean, if you take a bar magnet, you break it, okay, so you have a bar magnet has a magnetization. I mean, forget about these discussions for the time being. So you have a north pole, south pole. Now, what he found is that if you just break, and there was no polarity here at the middle. But if you break in the middle, there would be a south pole here, north pole here, and then there would be two magnets. Then he assumed that, I mean, this could be arbitrarily done, and then he assumed then that means there is no monopole, and there are only dipoles. So what happens is that these dipoles are tiny dipoles in a ferromagnet. Somehow they are ordered, so north. So this north and this remain disbalanced here, but south here and north here, so they cancelled, this way they cancelled, and so this went on, and here north south, and then south remained unbalanced, so we get a south polarity here. But north here was cancelled by north-south here. So this north was cancelled by this north, this south, and so on. So whatever tiny magnetic that you can find in the in your bar magnets, they must be very tiny, and they must be bipolar, and you cannot have just a monopole, because in that case this arbitrary breaking would not always give you the polarity. Then the question was, how is it possible, as we came to know thermodynamics, that we came to know that at any temperature, whatever order you try to maintain, noise, thermal noise will destroy that. Now, so then a kind of problem came, that how does the system maintain at finite temperature, say room temperature, or even at higher temperature, a kind of order such that they remain in a sense like this. Your bar magnet is not at zero temperature, and so on. And there is no, I mean, the system, I mean, you can take it, you can hit it at a higher temperature, it will destroy, it will get destroyed. At a finite temperature, that's, let us call that Curie temperature. At Curie temperature and above, so my magnetization is the net magnetization that I am seeing, this magnetization. If we make higher temperature, then somehow this naive picture that everybody would be completely random, and then there would be no cancellation, and everybody will cancel everybody. So there would be no local magnetization, no magnetization, global magnetization. I mean, locally, of course, these bars are there, and they will remain. I mean, these tiny Weber magnets will remain the same polarity, same strength, but they will be random, and they will destroy the magnetization, but only at a finite temperature. And if you bring back the system, you don't have to put any field, but the system will come back and have a symmetry breaking. I mean, spontaneously it will go to a phase where there would be an order at a finite temperature. So that was this order, this kind of thing was considered in thermodynamics as an order parameter. This and spontaneously this order parameter develops, and we have to understand how. And it was, the thing is, its variation, it was found all along is kind of analytic with temperature. It's an analytic function is kind of explaining the variation. But it was clearly established that not near this point. I mean, as you approach this point, the variation is no longer analytic. And for example, in the Curie-Weiss law that we studied in our early days, it is said that it is T minus Tc to the power half. Now that's the best analytic theory. It is actually closer to the real observations in systems, but this is the best an analytic theory could give, and that was understood much later that this is the best analytic theory. I mean, Landau showed that, and we got this thing. And since then, because you can easily see that if M, the magnetization is, if you think of thermodynamic system, it has a free energy which is function of temperature and magnetic field. This is spontaneous magnetization, so I will have the magnetic field 0. So this is, this is a function of, if I want to get M, that would be del F, del H, as H goes to 0. And it has T dependence like this. So T dependence like this. So that means I have not done anything. So now if I go back to free energy, it has this thing. So that means if I take with respect to temperature some derivatives, free energy derivative with respect to temperature will give me entropy, and then I can go to some kind of specific heat. It will try to show, I mean, if nothing else is there, then there would be an kind of non-analyticity coming. But this non-analyticity is not very important because free energy is magnetization square order. So that is safe. But somehow, suppose this is not 2, this is say 1/3. Say, if it is 1/3, free energy is magnetization square, so it is 2/3. And if I take derivative with respect to temperature, then it would have singularities. So all these things indicated, if in case it is not 2, then, or anything other than 2, anything say 2 plus minus epsilon, I mean half, instead of half, if anything else is there, free energy is magnetization square, because, okay, I don't want to go into that because your whatever Hamiltonian is, magnetization square. Anyway, free energy is magnetization square. So this kind of behavior here, if it is not exactly 2, it's not exactly half, is giving you an indication of a problem that you are approaching a singular behavior in thermodynamics. That means it's a very difficult thing, because usually Boltzmann probability is the best analytic function. You have to sum over all the degrees of freedom, and that's not, I mean, sum over analytic functions is not guaranteed to be an analytic function, but it looks like in this, at this point, indeed the sum, and that means you have to sum over the infinite system and solve it, and then you will only get that non-analyticity. So this was very important, that the order parameter goes to this, and it is half to the power half or not. Now it is another mean field theory. As I said, this thing was, and that's why this variation is very interesting. What happens to the order? This is called the order parameter, because that somehow in magnetic case that shows the order. That's a measure of the order. So we were, decades, several decades were spent in physics or statistical physics to find out this variation near this point. Now you see, you said that, very simply, your velocity is also coming to, velocity is velocity of the crack tip, even in this nucleation phenomena, is trying to show, this is a very simple mean field theory, is trying to show that there is possibility of a singular behavior here. And in case it is not exactly half. And that's also one important point to note, and that was also one kind of motivating thing for physicists to explore, and also experimental to check, and proper engineering designs were also dependent on that. We will come to that later. Now let us come to what Purushottam was indicating. Yeah, sure.
You say singularity. When you bring in singularity, are you suggesting that the stress field at that point becomes infinity?
No, if the stress square is always coming to the your energy calculation, and if stress is having a to the power half kind of thing, then there is no problem. If it is, but if it is not half, you see, you are saying that it is not exactly coming as sigma minus sigma c to the power 1. And if it is not sigma minus sigma c to the power 1, if you take derivative with respect to that, you will have problem. Like in temperature case we had. So then you are saying that this simple kind of indications are not going to be sufficient. If your velocity measurement says, no, it is not going exactly as half.
What I don't understand is, in this context, what does singularity imply? What do you mean by singularity?
Okay. Rather, I would say, here it would be a little difficult for me. For example, let us come to a thermodynamic system which has free energy, and free energy is the only thing that that is actually energy minus entropy kind of thing. Now, we calculate this energy, you calculate, this may be from like this kind of calculation, and entropy you have to calculate by the number of such things. And this, if you try to find out formally, is some kind of sum over some Hamiltonian you can find from. So this is called the partition function. This stress is sum over the stress from which this entropy comes, and that is from the Hamiltonian, and you take the Hamiltonian by kT, and that you take the stress of that. And if you take log of that, then you get the dimension of energy. Now you can see that this log or sum and exponentials, these are very, very analytic functions. It's hard to believe that it will ever go to a situation when, unless typical, t going to 0 or t going to infinity, there can be some similarities, but otherwise these are very, these are canonical examples of analytic functions, and you have summed over them and you have taken log of that. Again, an analytic way of doing it. At any finite temperature or finite, H may have some external field and so on, you are having some singularity because you are seeing that magnetization is going as, say, 0.31, and that's it. Suppose, this never goes like that. I think maybe here it goes like 0.49, 0.48 or 47 instead of half. Now you may say that this is wrong. Probably one should do accurately, and you will get it 0.5. If you get it 0.5, then it's fine, because your Hamiltonian, this Hamiltonian is actually, this energy is actually magnetization square order. So if it is 0.5, it is no problem. But if it is 0.47, then you have problem. And that is all about this kind of critical, I mean, we call it not only just a simple phase transition, there are criticalities involved, and you have to find out where these singularities come from. Now, it is not guaranteed that an infinite sum, the stress is an infinite, can be an infinite sum over all the states of the sample, I mean, and if the sample is infinitely large. And that means any finite sum approximation will never work. You have to solve the entire problem, and then only you can get, I mean, a sum over an infinite number of analytic functions is not guaranteed to be an analytic function. So you have to go there, and that means an infinite problem has to be solved. It's simple, this kind of mean field picture that I just do it for once and assume that everybody else is also doing similarly will not work really. And then only, I mean, you can understand this. And this was actually shown. And when experiments, various kind of numerical results in 70s or so, kind of proved that it is indeed correct. It is not 0.5. Then it was very, very intriguing because our foundations were almost getting shaken. Because you are saying that singularities are coming, which is not clear why from it is coming, because our foundations are like that. So either our foundations are wrong, or there was only one possibility. It's an infinite sum you have to do. And that was found out that it is indeed that. So then it is not such a trivial way of simple perturbative way, or such things would not work, at least in terms of this kind of parameters. And that was a story which goes over several decades. It's now part of many textbooks in physics and also elsewhere. So are there possibilities that even these simple kind of calculations are indicating that it's not so simple? We would say that it would, I mean, the experiments here are not so accurate, perhaps, I mean, and we will find another way of seeing that indeed there are some such indications, and indeed one has to be much more careful in developing that. Now let me come to another and more realistic situation. So only just in comparison, it shows that there may be some problem in case this is. Of course, this velocity will be some kind, eventually it will go to some velocity, but the problem is how does it approach zero when I am just putting marginal stress beyond the critical threshold stress. Yes? Let me keep that part. Okay, now let us have a sample which has various kinds of defects. And so these are the kind of defects, as you can easily see that, I mean, I couldn't prepare a sample for that. But anyway, you can imagine that the cuts were, the blade cuts were something like this in a paper. Now the stress release regions of this one and this one is overlapping. So, but still, there was an attempt to understand some phenomenologically observed distributions without, okay. So, and then of course there would be situations when these kind of things will almost percolate. I mean, of that time we cannot. So here, in this kind of calculation, when I am calculating whether this will propagate or not, I am not considering any other defect which may also have affected this calculation, because this energy was coming from, this energy release was actually coming also from this thing. So if there is some contribution, additional contribution from another defect, that was never taken. So in a sense, we are assuming that these defects are completely isolated. Somehow their stress release regions do not overlap. Let us do that still. You are no longer having, I have just removed, as Purushottam suggested, I have just removed the condition that there is only one defect. There are other defects. But I still maintain that those defects are still far off, so that these stress release regions, even here probably it is going to overlap, but it's even further, so that they are not overlapping. This is an approximation. Let us try to proceed with that. If we could do everything at one go, of course that would be better. We will come to that limit. We have to come. So suppose this is happening. Then the idea was that, then let us go to a different quantity. Suppose I put this sample is put under stress sigma, and I try to find out the failure probability of the sample. Now it was surprisingly, almost all the engineering textbooks probably give that in case of such nominally identical samples, you do not have a fixed things, because the failure probability typically has a form like this. This is 0, failure probability 1 is here, 1 is a line, and the real curve is somewhat like this. There is no sigma c in that sense. It is not like, do I have another color? Anyway, it is not like nothing here, and then it is this. This is what we did here. Here what we said is that there is a, if there is a, there would be a fixed length, that means this kind of sample, the system would not fail up to this, and that is actually what we were showing, that until sigma c there is no failure, and then it is failed. Failure probability 1. But you will see something like this, and identified to be like a situation probably is like this, and there was another thing. So suppose the volume of the sample, the same kind of sample, same material, from the same kind of production system came, has a volume, higher volume, then it is going like this. So this is, if this is V1 and this is V2, V2 is greater than V1. What it means? And if it is really true, I have another same sample. If it is like this, then in the infinite size limit, the system is just falling apart, any stress. Now this is precisely what Da Vinci observed. Even Galileo mentioned, Da Vinci observed that, he took the wires. I can't show the picture, that experiment, it is very interesting. You could see that paper. I am sure Purushottam can give you the reference or some such things. He was trying to measure the same wire, same material wire or same production kind of thing, that if it has bigger length, it has weaker strength. Now he could kind of tell that it is kind of natural, isn't it? It will have, bigger sample may have bigger void somewhere, and the bigger void will probably make a bigger, weaker point. And that, unlike, when I had this sample earlier, when it was intact, you see, if you would take the elastic modulus, or better, if you think of some this sample, and if you take the conductivity of the sample. So suppose this material is conducting and there is a non-conducting part. Then all these non-conducting part would have their role in the conductivity of the entire sample. elasticity of the system would be contributed by the major defect as well as minor defects. But somehow your failure property is an extreme one. It only looks for the weakest point, and the weakest point destroys the thing. So if you have a wire with many defects, your conductivity will be affected by all the defects. And then you have what in thermodynamics we call a self-averaging property. You average over the sample, you have a thermodynamic limit for the conductivity of the sample. But this kind of sigma c would help us thinking that there would be, like in a thermodynamic system, we had the transition temperature, which is precisely a thermodynamic result. In the limit of infinite system size, you have a precise thermodynamic temperature where the system becomes critical. But this says, if this is true, there is no such the thermodynamic limit is gone, because in the thermodynamic limit everything is brittle. I mean, everything has fallen apart. This is precisely what Da Vinci said, and then of course Galileo also mentioned that why do we not see such big animals, or our things do not go to an unusually large size, because with this kind of bone and all these things we would simply fall broken and die. So, and that observation, these failure probabilities are very well characterized. Distributions are there. Weibull and Gumbel distributions fit this. We will come to the distribution form. But you can see that distribution says that there is, I mean, this is I mean, how the extreme statistics is coming in. The extreme one is determining the strength of the failure. Now, smaller volume has a chance that a very big defect from local fluctuations will not, I mean, the cumulative effect of defects created in the sample would be very little. So that was made, I mean, I will come to a kind of hand-waving argument later. Let us have a little more kind of precise way of doing. So yes.
So in this analysis, when you have large number of defects, you are saying that as we go on increasing the volume of the system, then it will become weaker.
Yeah. Okay. So let me give you an idea. Suppose you have a line of length L. Okay, and it is of L number of bonds, L number of sides, or atoms can sit on these L numbers. L is large somehow. And if you have some defective, instead of an iron wire, you have some, say, manganese here, I don't know whether that will actually decrease the strength of the sample. Suppose this is possible because of your production system. Sometimes here there is a chance. So P probability of getting a defect. Okay? Then what is the probability that you have successive defects, because each defect is creating a void of this size. Okay? And each defect, and you are saying this defect density is very low, so another one will be here perhaps. So when you are considering this one, you need not think of any stress overlap due to this. That you could do. But there could be two successive due to fluctuations. That would be a bigger defect. The strength of this one will be much lower than this one. The strength here, one defect in this building anywhere which is big enough will be enough to, or on this floor, would be enough to take us all going down. So we have, what is the probability of that? Let us do the calculation. If we have L defects successively, where each defect has an independent probability of occurring, probability P, or rather say 1 minus P. P is the probability of not having any defect, and P, okay, or maybe let us make it simple. So P is the defect, probability. So I want to find L successive defects, and on other sides of these two there would be some 1 minus p square. 1 minus p here, 1 minus p here. Both sides there would be this. So this is this. This is the probability. This into L must be of the order of 1 to get one such defect. Okay? So what is the size? How to get the size L? L is the defect size due to successive things. Now this is precisely what Da Vinci had in his mind when he was trying to. This is called Lipschitz argument today. So Lipschitz tail argument. So to get L, what you do is you take log of both sides. L log p plus some 2 log of 1 minus p plus log L is 0. Okay, so forget about this term. This is not very important because this is somehow constant for this system. As I am increasing L goes as, and log p is negative, so minus of log L divided by log p. But log p is negative, so it is actually a positive thing. It grows with log of L, the sample size. Your p is not, I mean your production is perfect. Very little concentration of impurities can get in. But by that fluctuation, the defect of L successive defects will make a bigger void, and that probability goes with log L. And you can now put this L here, and you can easily see that it will be some gamma by log L or V, log volume. Instead of linear system, you can have a volume, and you will have to multiply with the volume in some sense. You have to, periphery will not be just 2 points, periphery will have something, but that's not important. Important thing is volume will go there. So as volume goes to infinity, your system is broken at any stress. So this was the thing. And this is what the engineering textbooks, when they give the Weibull and Gumbel distributions, actually show that. If you put there, you will get that.
I was confused because I thought for one crack it will depend on volume.
No, there would be, okay, so the idea is like this. In this sample, there would be this one, other one. I want to find out the biggest possible one. And I find that would depend on log L. So I put that, so biggest one will, as I said, I mean as you had seen, the biggest one actually was responsible for the first breaking. After that the sample is broken anyway. Why do you care for the rest of the group? Okay, so, so the biggest one, the first one that will occur will go as log volume, inverse log volume. Square root of that. So that says the system will break completely. Okay? So that thing we try to make a little, I mean, in order to bring to this form of Weibull and others, let us do it. So this, in order to get some idea of F sigma, what we do is 1 minus F sigma is the survival probability. That is much better because you can see that if you have many cracks like this, then instead of breaking probability, because breaking will require the extreme one. It is better for survival probability. Survival probability is when everybody will survive. Everyone must survive for the survival of the entire sample. So if this is, and if I assume that they are independent, then, and this is all the defects, so each of them must survive at that force This is the breaking probability of each of these. I do not know. I have to find out. But this total F, in order to find that F, I will have to do this. That 1 minus this is product of all of this. Okay? Yeah?
Can't we just check if the bigger one is surviving or not? Because if the bigger one...
Yeah, but then you have to find out the biggest one, or not the biggest, the weakest one. Because some linears will probably have, I mean, smaller, but this probably will survive this. So you have to get some statistics, and that's the idea of percolation theory and so on. How does this kind of clusters, or I mean the shape of the clusters and so on, that we want to bring in later, but very slowly. Okay, so, and this says, and this already gives you the idea where the volume will come in. Now this, suppose these are small, F's are small. If it is, then you can write it as e to the power minus sum over okay? And that says that I can write it as e to the power minus volume into densities of cracks which are failing under stress sigma. I can look for each of the crack, I mean, and then do it, but I just say that there is a density of cracks which are failing under stress sigma. Suppose I know that, and this has come. And you will see that the failure probability has already come, okay, something like this, that F sigma is 1 minus this, and as you can easily see that whatever may be the sigma as V grows, whatever may be the G sigma, gradually it will become smaller and smaller. I mean, so you have already got this thing by seeing that it is 1, so F sigma is now 1 minus this thing, okay? And the volume has come there. But now we have to find properly what is G sigma. Now this is difficult because what we know is, I mean, there are two possibilities. Okay, yeah, I think I should go back to magnetism again, just as an example. I mean, let us go back because magnetism is perhaps, yeah? Okay. Okay, so 5 minutes more. Let me introduce the okay. Yeah, percolation would be a better thing than magnetism. I thought it is better because eventually we will have to use percolation. Okay, what is percolation? Let me introduce. It is the same spirit. Forget about these things. I am not really continuing now this discussion. We have come up to this. We will have to find out something. Now, let us do one thing. Most of you are percolation phenomena. Now this is actually we just discussed ferromagnetism, which is of course temperature driven, I mean energy driven and so on. Percolation is a geometry driven transition. A kind of similar things were observed. This was great. Of course similar. It has again singular properties in its generating functions, but we will come to we will not need all the things. It is essentially like this. If you have a sample, say, you have put under some, sorry. And maybe you have put some ammeter here, okay, ammeter is not. Suppose you are putting some random conducting bonds here and there, or some conducting dyes I am throwing. Now, somewhere there would be bigger samples, bigger conducting paths. I mean, these are conducting bonds I am throwing. And still, there is no current. So I am plotting current measured by this ammeter against, say, the probability of throwing these conducting bonds. Let that be called P. Now it is clear, if P is 1, I mean P maximum value can be 1, and minimum value can be 0. I have not thrown anything. Now if I put all the bonds, conducting bonds, then there would be conducting lattices. Everything will be conducting. And that will have the maximum current that you can imagine, because whatever conductor you have used, with that, the lattice, I mean, no further change. So it will be 0 here, and it will be 1 here. I will be 1 here. Now the question is, does it do like this? What is your intuition saying? There would be this porous medium calculation, I mean studies, I mean how to recover oil and things like that. Porosity have to go to beyond a limit, beyond which there would be a percolating path channeling towards the oil reservoir, and so you will need, there will be many more important discussions later. What is found is that, I mean, okay, you can imagine a very, very odd fluctuation, which is in the infinite limit is impossible, but small system. Now, is it not possible that if it is one layer system, say 1 by 1, then of course just one bond is good enough to. So you think we should go now because the tea is getting cold.